I'll just wait for a few minutes and then start. We'll just wait for others to come. Okay, we'll just review what we covered last week, right? So, starting from cost casting. So, essentially, cost casting is it takes a variable which is constant in nature, right? But it then temporarily removes the constness, right? So that it can change the variable it is actually pointing to. So, let's say it takes a pointer. So the pointer itself might be const. So in this example, we have const character pointer, right? So this constant string itself is a constant, okay? But the variable it is pointing to, so here in this example, the hello world, right? It it can be edited, so it temporarily removes that constness. Okay. The print const cast and then putting the character pointer. So it's essentially a character pointer, right? But the print function that we wrote, it only accepts character pointers with, let's say, the parameter string. So now it cannot uh, accept a const character directly because it's not compatible with this data type, right? So there are two ways to resolve this. One is we'll overload this print function with a const character definition again. But the downside to this is we have to repeat the same code twice now. So once I have to write for the non-const part and another with the const part, right? So essentially to avoid rewriting and repeating, okay, one can choose to use const casting, right? Where the const casting takes the same character pointer, takes the const string, right? And then the whole thing essentially works as if you're passing a const character pointer, right? So this is the C++ style. The same thing you can achieve using the C style by just using the brackets and type casting it to character pointer. Again, I'll reiterate the main difference being that in C++, the intention is clear. Okay. That's what the heavy emphasis is on. Like you are typecasting, yes, but what is the intention here? Okay. Here it is also doing the same thing, but the intention is sort of lost. Okay. Then, right. So seeing another example. So we have a class A. It has a private member I. Then it has, so we also define public members. Okay. So the first of all, the constructor itself, it takes under I underscore, and that same I underscore, we set I to that value. Okay. Essentially, the constructor takes a value, an integer, okay, in this case, and sets the internal member variable, okay, the private member variable to it. All right. Then we write a getter function and a set function. Okay. These are basically getter and setter functions where the getter function has access to the internal member variables, and normally we don't want it to be exposed outside. Okay. So we write wrapper functions like this and access those variables. Now, this function is const. Okay. The reason being, ideally, this function should not change the variable, right? Because it just gets the value. It's a getter function. Okay. So because of this nature of the function, right? Um, it yeah, sorry. Because of the nature of this function, so here in this case we can use the const. Okay. Setter function, yes, we cannot use it because we essentially want to change the variable. Okay. So hence we don't use it here. Okay. Like before, we'll have the print function also, where it will take the string and print it. Okay. And then finally, coming to the main function, we have the constant const string, okay, with the constant string hello world. Okay. Then we have the like try to print the const string again, it will throw error, right? Because it doesn't recognize. So we can do a const casting. All right. The next thing what we do is we have the const A. Okay, so A is the data type. That's the name of the class. So the small a, the variable. All right. And yeah, okay. So that's the name of the object. And then we're passing to the constructor of it. That's what we're defined in this line 7. Okay. So okay. So this is how we define the object of data type A. And also we are saying it is of const nature. Okay. The getter function is fine. The nice thing about the constructor is that when the object of this set of this class gets created, the value gets set. Okay. So one need not worry about uh creation. I'm sorry. Excuse me. Yeah. So like I was saying, so you have the object A, small, like the name of the object is small a. Okay. It takes the value 2. And while this object was created, the member variable I was initialized and set. Okay. Now the constness of this object determines that we cannot change the object's members. In a way, you can think that way because it is const nature. Okay, but ideally, if you think the integer I originally is not of const nature. Okay, again, same conditions are satisfied for us to use the const casting, right? So if one tries to so in this line, so getting the value, it's not an issue. Okay, so that prints the internal value. We'll get 2 in this case. Okay, if we try to set the value to 5, then we run into a problem because of the const nature of A. So what we can do is temporarily typecast A, okay, to const, um, like using const casting, right? Then set it to 5. So here we passed A as the reference. Okay, so uh, the small a as a reference of data type capital A. Reason being, we want the specific this data to change. All right. So that's how the expectation of syntax in const casting works. Okay. And then if you try to print the value using the getter function, we'll see the changed value. Okay. So if you try this way also, sorry. So you try this way, it actually throws error, right? Okay. 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 Moving on to the next example that we saw, oriented print cast. So essentially, this one works. The way this typecasting works is it takes the same sequence of bits that you have in, let's say, a data type. Okay. So your data type essentially contains 32 bits or 64 bits, right? So let's assume it has 64 bits. So there's a sequence of ones and zeros in that data type. Okay. So that sequence is preserved or maintained, but the same sequence interpreted in one type of in one definition of floating point number gives you a different number in, let's say, decimal than if you treat the same sequence as a 2's complement, okay, in binary, and that will give you another decimal number. Okay, so the same sequence of bits can result in completely two different real numbers, okay, in decimal, right? So Reinterpret cast essentially is used to uh, convert one from the other. Okay, so if we take the example here, so L, the long, if you store 8 in it, okay, so that is essentially storing it as an integer, okay, 64-bit integer, right? Now we have D equals to 7.5, okay, and I make a pointer D, ptrd, as a double pointer and pass the address of D to it. So essentially, ptrd now points to D, okay, and which has 7.5, right? So I can, if I try to set L equals to ptrd, okay, so that can actually think that is okay. Yeah. So this was week 8. Right. So all this was fine. We just print this on C. Okay, fine. Okay. So this throws an error. Reason being, it implicitly cannot just convert one data type to another. So if you think about it, a double pointer, okay, is essentially a pointer which stores an address, right? So ptrd essentially stores an address, and its data type is size underscore t, okay, which is the sort of like, you can think of like the largest integer size one can have in our system. So that will be again 64-bit integer. Now, technically speaking, the size of ptrd or the bits it holds, 64-bit, is the same as along, but implicitly typecasting, okay, is not allowed. So if you go with explicit typecasting, that is fine, okay, and that is allowed. So you can typecast pointer D and store that in L. Okay. And printing this, we see the address of D, ptrd. Okay. So you can just run the same thing again. So address of D and the ptrd now contains, like, they should have the same address, right? So we essentially, because address of D is we're accessing using the ampersand operator, ptrd should have that address because we store it. Okay. And if you try to print long, now it prints some other number. It doesn't print the hex value. Reason being, yes, we store the same sequence of bits in L, okay, but remember it is treated as a 2's complement number. So the same bits now are treated as a long, okay, and a long is an integer. So when you try to print L, it prints the same number in decimal form. Okay. Now this is the C style, okay, but the intention again is not clear as to what we're trying to do here. So if you do the interpret cast, okay, pass long to it and pass ptrd as the argument, okay, and then we can store it to L. Okay, so that L now, sorry, in that L now, if you try to print, it also prints the same thing as we see here, right? And if you go with the size of long, we see it as 8, as in 8 bytes. Okay, I think we can do the same thing with this also. So size of double pointer, I hope it should work. Let's check if that is allowed. Okay, good. So the size of double pointer is also 8. So essentially both of them are 8 bytes or 64 bits. Okay. Size is same, but uh, it depends how you're interpreting the same sequence of bits. So that's essentially the summary of this. Okay. So you can use the reinterpret cast for this situation. Moving on. So you can have like static typecasting, where let's take an example actually. So let's say I have an integer I having 7, a long L with 10, double, we call it D with 2.5. Okay. So setting I equals to D will have implicit typecasting, where you are taking something with a longer bits to and shortening it to store it as an integer and having it as integer D. Okay. It's explicit style. The end result is the same, but the way you get there is slightly just different. Okay. It's an implicit typecasting method. Here we did the explicit way. Same thing one can achieve by doing a static cast. Now this is plus plus style. Okay. We pass the variable that we want to get the data from. Okay. As the parameter. We pass the data type that we want to convert to, which will be the I integer, right? And then store it to I. The nice thing about this is that again, the intention is clear and we are here that we want to typecast one data type to another. Okay. And but in this case, we do not preserve the sequence of the bits. We're more focused on the actual value it contains. Okay. What I mean by that is, so if I'm converting a double to an integer, the idea will be that it should um, drop the fractional part and give you the integer part itself. Okay. That's sort of the essential idea here. And that's what the static casting does. And if we try to print IND again, we'll see the final result. Okay. We can actually run that and see. No. So yeah, so first one's print 7 as expected. Okay. After typecasting, it prints 2 because D has 2.5, right? And D itself has 2.5, so that gets printed. If it again static cast I to D, okay, we can do that. So I contains how much 2? Now D contains that same. Okay. So the reverse way also one can do the type static casting. Okay. Right. Okay. Yeah. So that this takes care of example for static casting. Now let's take another example where we have I equals to 5, L equals to 12 along. Okay. So this is an integer and a double variable named D as 3.2. We define ptr I, ptr D, ptr V. Okay. I will have it. I is the integer pointer, that D is a double pointer, V is the void pointer. And we set the addresses of ID to this. Okay. Void pointer anyway. We can set initially something or not. Up to you guys. So in the example, we set ptr I to V and ptr D equals to V. The reason being, why does it work? This is, we're not explicitly typecasting anything, right? So this is implicit typecasting by syntax itself. Okay. But now, is this allowed or not? It is, because essentially we're saying you take the same pointer that I have or some address and D also and store it in V. Like in one case with integer, another case with double. Okay. But end of the day, both of them contain addresses and those addresses you're storing in this variable. The only thing that is lost here is the data type it is pointing to. So void pointer is okay with that as long as its only thing is to just store data anyway. So it doesn't care about the data type. Okay. So that is okay. That's all right. We try to do the opposite with the implicit typecasting, that won't work. Okay, as we saw in previous examples. If you want to do the achieve the same thing, one has to typecast it. Okay, and that's typecasting can be done this way in the C style way, or the double also the C style way. Okay. Second thing, or the C++ way, I would say, rather say, is doing the same thing is have a static cast. Okay. So you have the C style, then you, the C++ way will be to have static casting. All right. Have integer pointer, double pointer passed as a template parameters, and ptrv as the uh, default, the parameter value. Okay. All right. So moving on. Today's class will cover templates. I missed something. Okay. Let me see one. All right. Okay. As usual, we'll have the IO stream to print. Let's say I have a function max. Okay. It takes integer a and integer b and essentially returns, okay, one of them. I think you can guess which one, whichever is the larger one. Okay. So to compare, you can just compare a is greater than b. Okay. So the ternary operation can be really useful to just do this in one line. So we'll return something. So that something comes here after the question mark. So let's say I'll write it this way. I'll go over this one by one. So the syntax goes as, so first so the ternary operator compares, there's a Boolean part here. Okay. So a greater than b. If it is true, okay, so it will return a. And for the ternary operator after the colon is the else part. If it is not greater, it will just return b. Okay. And the whole thing can be written just one line. Okay. Same thing one can achieve uh, through by doing it this way. This is the second. Return. Okay. Same thing, but return like a if else statement. Again, one doesn't need to do the whole if else statement. You can just use ternary operator to do the same thing. Now imagine I wrote this function to compare A and B, okay? And the inputs here are integers, and the output is also expected to be integer. The user again maybe wants to write the same thing, but for double. So it has to write it again, right? So because C++ doesn't allow you to just have uh, this same code work for all kinds of data types. It will only accept integers. So what will happen is you have to give it a double A, double B, start the body, okay, do a return A greater than B, question mark, A colon B. So if you notice, even if the input variables and output variable are double, the body of the syntax doesn't change, right? You still compare integers this way, you still compare double floating point numbers this way, and return whichever is greater. Now, since the body doesn't change, as in there is a scope of not just repeating code and again, right? So it sort of just gives the insight. It's just an idea. Okay. So here exactly for these kind of cases, yeah, for exactly these kind of cases, templates are quite useful. Okay. Let's take another example. Yeah. So let's take another example where So write it this way. Yeah. So we'll define the IO string header file again. So include that. Now instead of just sorry, instead of just using functions, we can define a macro actually. Define a max macro which takes A and B, and the definition of this macro is this. Evaluates, it takes like A as a variable, B as the variable, compares them. Okay. And then the ternary operator returns one of those. Essentially, this max operation, okay, macro takes A and B, it compares and just sets A or B. So wherever this macro is called, it will just set it during compilation time. Okay. Right. So now the same thing complete. I can call the main function. Okay. And let's see out max 1, 2. That's it. Mhm. The nice thing about this approach is the values of A and B themselves need not be known at compilation time. Here, I just gave an example. You can have variables which are input from some other for let's say it's for some function and call those max A and B. It will just replace max A and B with the expression of this ternary operator. Okay. Because of that, whatever is the value of those variables that will be set, let's say after compilation in runtime, that is absolutely okay because the expression will just be there for it to evaluate. Okay. Right. So because of this, this expression works for both integers, double, everything. Okay. Again, for variables which are compilation time or runtime. All right. So this is the usefulness of macros in this particular case. Right. And I have like this. So 1.2 and 4.5. The nice thing is that again, like I said, here it could be integers, it could be floating point numbers, it doesn't matter. It need not be the compilation time. Right. Okay. Right. 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 Sure. Compilation. Okay. Okay. Let's take example. Separate one. Yeah, I cannot compile this because I don't write the main function. So I can define, let's say, I need not define anything. Actually. Let's call the function. Just actually copy the sending. Okay. So if you think about it, here I used it as a capital M small ax, but effectively if you think about see this, it looks like a function. So this macro essentially looks like a function, takes two inputs and then replaces with the ternary operator, does the job. The goal is that we want something like very similar to this with C++. Okay. As we see here, we have to write different ways to overload the function. Okay. Right. So because of this, or have essentially various definitions of it. So because of this nature, okay, templates are introduced. So just come to them now. For that, I'll just run this. Okay, so 2 and 2.5. So passing in, we see whichever is the larger one. And the second example, so we have again 2, 2.9. Okay, all right, it works. Both the cases give the same answer as this should. Okay. Now let's see how we do the same thing, but with templates now. We'll have include IOStream. Um, I'll write the main function first. Let's say A equals to 7, B equals to 9. So then P is, let's say, 3.4. Okay. And Q is 7.8. Okay. So let's say I call the original, I'll write the new max function, but say call the max function. I would like to pass AB, okay, print, and then get the output. I also want to pass P and Q without worrying about these data types and expect sort of the function to just. So that's sort of the idea. Okay. Now let's see how you achieve this. So to do the uh, like write the same function, but for two or multiple cases, we'll use templates. Okay. So this is the syntax for it. We will write this type name, let's say T. We'll define a type name T, which will be the template parameter. So T becomes sort of a placeholder for all the data types. Okay. So TA, TB, or maybe I'll just make it XY. They just have to return X greater than Y, conditional, then return X or it's Y. Another line. Okay. Now, the nice thing about this is it will interpret this max function, will interpret what's the data type here, okay, of the inputs X and Y, or you can mention it explicitly also. Either way works. Okay. So if you try to print this one, okay, so this is template 3 example. It prints 9 and 7.8. Right. So the first max is treated as an integer. So this T here is a variable, and the name in general is a type name. Okay. So all these data types, we can have like a generic name for it. Then it's themselves like a data type. Okay. So the T, capital T here will be integer for this example, double for this example. For capital T as integer, it will be integer max, integer X, integer Y. So it takes two integers, returns an integer. The definition is exactly the same for both. Okay. Doing the same thing with doubles. Okay. So passing P and Q, max will then know which one is greater, which one is smaller. Right. So max will have like P greater than Q, then P comma Y, like P colon Y. Okay. Again, the definition doesn't work, the body doesn't work. Okay. Doesn't change. Okay. It's the same thing. Just that the data type just changes depending on which one we're using. Same thing, one can also write it more explicitly. Here it implicitly knew or deduced what data type we are actually passing. But if you want to be more thorough, you can do it this way. Call the function max, okay? Pass the data type, integer, okay? Because we want to pass AB, all right? Same thing with PQ. And swap integer to be done. So printing it, see the same answers. Okay. The answers essentially won't change. It's just that how you want to write depends. Here I explicitly mentioned the template parameter types. Here it's just reduced it. Okay. That's only the sort of the difference. Okay. We can take it little further. Okay. So let's define a double. Um, MLN m equals to x of a comma b. Okay. Integer n PQ. Right. Same thing. Now I'll just print them. The PQ should return a double. Okay. That's stored in n now. AB returns an integer that is now stored in m. Okay. So if I try to print n now, let's see the output. I try to print n, then we'll see the output. Okay. Right. So essentially what happened here is I had a return of integer. Okay. So ABs are integer and the return is also integer. Sorry, AB will be whatever data type, the return is also the same data type. So for the max function, integer, the bigger one is 9, so that one is returned. And now that is stored in a double. So for low numbers, there is a essentially if you uh, uh, refer floating point numbers and two's complement if you are not familiar with them. So there, the double floating point number can exactly represent integers to a certain range. Here it is small enough to fit in that range. So 9 is stored in M. When you try to print it, it prints 9. Okay. Second example, in the further one, we have the max of PQ. Okay. So P is 3.4, Q is 7.8. All right. Then um, the bigger of them is being 7.8 will be written as a double, but we are storing it as an integer. Okay. So typecasting will happen implicitly, and that's what we get. Okay. So yeah, I'll just mention implicit typecasting happens. Okay. Okay. Um, Moving on to the next example. Yeah, right. So moving on to the next example, we look the same template idea in classes. So let's class templates now. Include string. We have template, type name. I have the class max. Okay. Then instead of just functions, you can even capitalize classes, right? So we'll have the same some data type capital T represented and define A and B, okay, as a member variables. We'll have public or the constructor for the max class will take A, will take B, expects essentially the same inputs in all the parameters it takes, F, A, and B. Okay. And then the we'll set A to A and B to B. For this, we can use the explicitly this operator. Okay. The axis is A, set it to A. In this example, we have input as small a, and small is also a member variable. So in the context of this constructor, the right hand side A is this parameter. And referring to this pointer, right, THIS, with an arrow operation to A, essentially represents the A belonging to this class, which is with this thing. Okay. I hope this is clear. We can do the same thing with B. Okay. And then make a function max. Okay. For the same data, B max. Have the return. Yeah. For this, now we can return the same ternary statement that we have been seeing. Have a question mark. If A is greater, then we return A, else return B. Okay. Yeah. Syntax wise, don't forget the semicolon when you like complete the scope of the class. Okay. We'll have the main function. Now we'll just call the max class. Okay. Remember to define this, you have to pass the template parameter. Okay. So we'll pass integer, make a class called just m. Okay. Pass, let's say, one true. So now the class is defined and everything, right? Now we can call the prints, like printing the statements. So m dot max function. And because these variables are set by constructor and everything, we don't need to worry about passing them again. So we can just call max, and the object's own function will know what we are doing, want to do also. So this will give the max of those values. Okay, right. Okay. Oh, right. Right. So yeah, like I was saying, you have to pass the template parameter while constructing the class. Okay. Let's say one doesn't do it and then just constructs it plainly. That also sort of works. The reason being, the max function takes, don't worry about the calling the dot max function. The max class itself has a constructor. The constructor expects two same data types. Okay. And because we give them that, this is also allowed. Okay. Right. Okay. So yeah, now moving on. Yeah. So taking another example, having include have stream benefit pipeline P1 pipeline two plus minimum. Okay. Now instead of just taking like a constructor, okay, we can have two different data types also, like T1, T2 data types, and construct template from that also. So let's see that. So we had the max function. Now let's take the main function with type T1A. Okay, define type T2B, a public uh, part, the portion of the class where we'll have the main as the constructor, T1A taken, T2B also as an input parameter. Then this function, this HIS pointer to A is set by A, same thing, B, right? T1A, T2B, A, B, all right. And then finally, we want to return as T1, okay, the main function. This one will be, okay. So this one will be basically a return, okay, less than it, question mark. Sorry. If A is less than B, we return A, okay, because that's the smaller number and the function is minimum. So essentially, that's the sequence. We change the operator A less than B to for minimum, for maximum it is A greater than B. Okay. So now we can have another class. Okay. Yeah, pretty much the same thing. We'll call it max A B. Just it. Okay. Let's uh have the same class, max class here itself. Okay, so now the main function. We'll have the max. Let's yeah, I mean, let's have the original thing itself. That's okay. Essentially, what I'm trying to say is you can call the max functions. Okay, so have those. Other than that, we can do it with the main function also. So let's do that. So main, we call it, we'll say obj object text parameters. Okay. So that's a 2, 3.1, and end. Okay. Now obj dot main should be good to go. Okay. I don't know. I'm not sure if it will interpret those data types implicitly, but we can check. I mean, that's okay. Yeah. All right. Last step to two. Um, oh, okay. It's just outside. Right. So some issues which will be, yeah, okay. Needs to be templatized. Again, it's also part of the syntax. We can't just have a T. A T in itself doesn't mean anything. It has to be a type name T or something. Okay. So if you're using a template, then that's what it is. So yeah, it interpreted two, right? So the minimum of um maybe I'll just 1, 2, 3, so maybe 4. Okay. Then print it. Yeah. Right. So if you think about, okay, maybe this one becomes a little trickier. I'll do it before. Yeah. Right. So what this minimum object does is it interprets the two input parameters which from the constructor, right? So it one will be T1, another will be T2, right? So basically these are two different data types. So for the first one, it sees dot as a decimal. So it assumes it will be, let's say, a double. So these two are double, right? And a comparison happens and everything. So that's fine. But if you think about it, in the minimum function, there's a return type. Okay, so there's a return and there's a return type T1. So to return always to the first value. Okay. Hence, if I have both of them as double, the answer will also be double because the first one isn't double. Okay. Now, let's say I change it to 3. Okay. So the first answer was 3.1 because this wasn't double. Let's say I change it to integer. It will be like it's actually double, but it can represent exactly. So it just prints without the zeros. Okay. So like, not as in 3.0. Okay. But if I have first one as integer, a second one as um with decimal as an floating point number, the lesser of them is 3.1. Yes, but the print won't be as such. It will print as 3. Okay. I hope you understand the difference. The reason being the 3.1, since it's a lesser, yes, that is true, but the return will be in the data type of first one, which is integer. So 3.1 implicitly gets like casted from double to integer while printing this. Okay. Second example, I think it's straightforward. We just have the same example as before. Okay. So that is, I think, fine. Okay. We'll take another example. We have include file string. We have the vector class. The bit type name. Sorry about that. Yeah. So we'll define another class. Call it A this time, which will have a standard vector. So hence the vector class being given. Interestingly, now because vector class themselves, since we saw in the start that they are templatized, so we can just have them pass the same template as of the class into the standard vector. Okay, and call it, let's say, B. In the public portion of the class, we'll have a void function. We call it an init function. Okay, it will take size, let's say, underscore t, n. Basically, the size to which this vector needs to be initialized to. Okay, and let's call resize with n. Okay, all right. The reason to do this is anyway, the vector is not accessible outside, right? So anything we want to do to the vector, we have to do through functions accessible outside. So hence, init function is created, which resizes the current vector. Okay. So it doesn't matter if it is not allocated any memory initially, it will just allocate that memory. If it had some different size, it will set it to the new size. Okay. So integer main, integer, integer dot init. And let's say I pass 12 to it. Okay. So A is the class, and we want it to be templatized as yeah, exactly. Since we did not write another important thing here, we have to specify the template. All right. And the name of the object is obj. That's I think evident. But the important thing is you have to specify the template type. Okay. Now it creates a standard vector of integers. Okay. With the name v. When we call init and pass 12 to it, it will create 12. It will create basically resize the vector to hold 12 values, and the values happen to be here integers. Okay. Again, it becomes very clean to have classes as templatized because the data type itself can be for a lot of the member variables of the class, and you do not need to write this code for multiple times for different data types. Okay, all right. Okay, and also let's cover another important topic, polymorphism. Okay, so we saw previously we have a base class. Okay, so for example, this itself, let's say. Um, this is let's say the template, the derived class. This is a templatized class. Can derive this class here from let's call this as B, public B, and the base class could be just simple uh, class B. Okay. Yeah, that's it. It's pretty much empty. Yeah. And we can have a main function. Returns here. If not made any mistake. Okay. Uh, run this one itself. Great. Oh, no, my bad. Sorry. Should be class template. Okay, good. So this works as expected. Let's just do it. All right, I did not include the header files. My bad. We need the vector class because we use parent vector. We also need if we think of printing things at all. Okay, great. So essentially this, okay. Um, I'll create uh, a base B object, okay, and now the base B is not templatized, right? It's just a base class point. It's just a base class. My class D is derived from it. It has vectors, it renates and does many things. What I can do is since it is the yeah, okay. So class D, I can define D, right? But one has to be careful because I have to give it some data type. So it could be integer, it could be double, so on and so forth, right? And remember, because of inheritance, you can actually set uh, one class to the other. Right. What I mean is not one specifically. You can set the base class actually. So you can set it like B equals to B. Can't have both of them, but let's say this one. Okay. Uh, base, yeah, sorry, my math. Let's set the B. Okay. So essentially what one can then do is let's say T is some type that you get. Okay, so I'll have the not in this function, but let's say you have if capital T equals to sorry about that. Yeah, if capital T is integer, then what I'll do is I'll create B. Okay, I'll just have them in comments for now. So I'll create B, which takes integer, right? Or you can just have capital T here. Okay. Actually, no, because the capital T needs to be compilation time. And another thing, very important part about templates, the template parameters themselves need to be compilation constant. Okay, at compile time, they should be known. Okay. And another very important property about templates is that if you think about functions itself, this whole thing, whatever templates you make, right? So for example, in this case, yeah, this one and the whole class is there, right? Okay. I always made classes. Oh yeah, no, this one, yes. Uh, right. So I made a function, right? So template function max, which takes x and y and returns the maximum. This function does not get compiled if max function does not get called at all during compilation. The nice thing about templates is that when they're first time called for compilation, so let's say from this in this example with integer passes parameter, it takes integer, generates the code for integer for the whole function. It encounters double, generates the code for it. So because they will be called, then only it makes the code. It is actually quite efficient in way from a memory perspective. Okay. And again from compilation also, because if that function never gets called, you don't need to worry about um, uh, like compiling it anyway, right? Right. So why even bother compiling something? Sorry. Why even bother compiling something which will never get called in the code actually? So this piece of code actually doesn't exist, okay, until this call happens. Then it actually compiles the whole thing and has the definition, body, and everything for integer. And when double gets called, again a copy of it with double. So if you comment both of them, this piece of code does not even have any. There's no max function at all in your executable. Is what I'm trying to say. When you have both of them commented, okay. So as in all of this, what I mean to say, like whatever you're calling max. Okay, I hope that idea is clear. Yeah. So going back to polymorphism, so we'll have say some t coming from as a parameter, not as a comparison constant, but maybe let's say runtime. Okay. So this type, this says integer, then I'll set my base class to d integer d. So this will create uh, integer. So I will not d, I just with the constructor. It will create my derived class. Okay, and now I can set b to it. The nice thing, what happens here is I can use the same base class for all kinds of data types. Okay, so let's say d is double. Okay, so then it will create e. Okay, e with double. Okay, then I'll send it. Right. So the derived class will be created. Okay, the whole complete class will now be created with double. Initially, it was created with integer, right? Created with double, and the same created object now can be set to B. So the same B, if you think about it, because it being a base class, can be used for all derived class templates in general. Okay, that's the usefulness of templatized classes. Okay, where you can how to put it, where you can just have a single object playing the role for all templatized derived classes. Okay. Now, if I want to, I can then just do this way. B dot. Well, there is no init, but okay. I can't call the variable. Okay, but then in that case, what I'll do is I'll just have a sort of like a virtual function. So maybe void int which takes size, and that's it. Yeah, doesn't have a body. Okay, it just takes size and ends. Now, because we have another definition of init in the derived class, it will just override it. Okay, then we can call t.init and pass, let's say, some value n, which is again, let's say, comes from some function. Assume here this is inside some function. It takes e and n, and we'll just make this as a body. Yeah, that's it. This and the definition here. I should not change anything because I have all this in comment. Okay, so essentially, this is the idea where you can have multiple template pointing to the same, like multiple templates of derived classes pointing to the same base class object. The reason you want to do that is Base class is easier to, let's say you want to move around, as in you don't want to worry about what what object you have created for the derived class. Same base class you want to just reuse and many places. So this is a very useful nature of C++. And this whole property that we see just now is called polymorphism. Okay. Your B object essentially has sorry about that. Your object B essentially has various faces in a way. One can think of that depending on whichever derived class template that one passes. Okay. All right. With this, I'll yeah. With this, I've covered topics that I wanted to cover today. If you guys have any questions, you can feel free to ask. Yeah. Okay, there are no questions. I'll end the class now. So next class will cover more of the topics. There'll be some ideas about operator overloading and input and output of file IO. Okay, which is also very important in C++. Okay, so right. So see you guys in the next class.